All right, everyone. My name is Joe DePaul. I work here at Oracle on the Helidon project. And today we're going to talk about kind of our experiences using virtual threads in the real world. If you've attended some other talks this year that discuss virtual threads, you will have heard them mention that they're great for highly concurrent, high throughput servers. And that's exactly what Helidon Web Server is. So we're going to go through our experiences and discuss some lessons learned as well. I'm joined today by Romain Graycore, who's in the front row here, and Danielle Ketz. So they will be available for all the difficult questions later. The agenda today is I'll start with a brief introduction to virtual threads, a brief introduction to Helidon, just to make sure we're all on the same page. I'll bring those together and talk about virtual threads in Helidon. And then we'll discuss some lessons learned and tips for using virtual threads. And then a little peek at some things that are next that you may have heard about and some Q&A. So first of all, with virtual threads, how many of you have actually used them and feel pretty confident in understanding what they are? Okay, so a few folks. So good. I'm going to go through this pretty quickly, but it will get everyone up to speed, kind of a level set on virtual threads. So this is now JEP 444. Virtual threads are JVM managed lightweight threads that help in writing high throughput concurrent applications. So lightweight and JVM managed are the key points there. They were preview in Java 19, final in Java 21, and even better in Java 24. So now in Java, threads can be either platform threads or virtual threads. Virtual threads are compatible with platform threads from an API point of view. So if you have code that creates and uses platform threads, that code is API compatible with virtual threads. So making the switch at that level is pretty straightforward, although there are some considerations that we'll talk about. You can have a lot of virtual threads. Millions of virtual threads. So we have benchmarks we run where we load our server like crazy, and we are creating millions and millions of virtual threads, and they work great. We're really pleased with performance and stability. Even latency, the scheduler for virtual threads seems to do a great job. We're really thrilled. And then virtual threads, they're scheduled onto platform threads to run using platform threads from the fork join pool. And we're going to talk about that a little more. So when a virtual thread runs, it mounts to a platform thread. And we often call that a carrier thread. Okay, so the virtual thread is ready to run. It gets scheduled onto a platform thread. That virtual thread will then run on that platform thread until it performs some blocking operation. Blocking operations are very, very common, right? As soon as it performs a blocking operation, the virtual thread is unmounted from the carrier thread, and that frees up that platform thread for another virtual thread to be scheduled on top of it. So the key here is that we have been trained in the past not to block threads, right? That's a mantra, do not block threads. But with virtual threads, blocking is okay, and in fact encouraged. So it's a great mind shift for doing server applications, and we'll show some of that. So this code here kind of illustrates this. So you have a virtual thread that's running, say it's running this code. It generates a random number. That's a non-blocking operation that executes. Then maybe you go to call a remote service using an asynchronous HTTP client. Most HTTP clients these days are asynchronous. So that returns back a completable future. And that is non-blocking. So your virtual thread continues to run. Then your virtual thread on that completable future does a get. So in the past, we have been told, do not do get on completable futures, right? That's a blocking operation, that's bad. But for virtual threads, it's good. So you just do this get, you can block on the result from the client. The virtual thread is then unmounted from the carrier thread because of that blocking operation. And that platform thread is now available for other virtual threads to be scheduled onto. So you're not blocking the platform thread, you're blocking the virtual thread. At some point in the future, that completable future completes, and that blocked virtual thread is unblocked, at which point it will be scheduled onto a platform thread. And then it continues to run. So I won't beat a dead horse, but you can see the power here, that when you do a blocking operation, it blocks the virtual thread, not the platform thread. It frees up the platform thread to be used by another virtual thread. I said that virtual threads are API compatible with traditional threads. That is true. There's also a couple new APIs. You can inspect a thread and see if it's of type virtual or platform. There is a new executor, the virtual thread per task executor, which just keeps on handing out virtual threads. And then you can check if a thread of virtual, thread of platform creates virtual and platform threads. Thread is virtual tells you if a thread is virtual or not. So the big takeaway here is that with virtual threads, threads are no longer a scarce resource to be carefully pooled and managed. Instead, they are an abundant resource that can be created as needed to handle nearly unlimited concurrent tasks. So if you're in Ron Pressler's talk earlier today, he mentioned that. Your focus shifts towards just allocating virtual threads as you need them to execute concurrent tasks. Okay, so that a brief overview of virtual threads. We'll come back to virtual threads. I'm going to do a brief overview now of Helidon. So how many people have used Helidon or are familiar with it? Okay, a couple hands. So I'll do this pretty quickly because we want to get to the meat of the presentation. So Helidon is a framework for developing microservices. I say micro in parentheses because you can develop big services with it too. You go to town. But if you're familiar with Spring Boot or Quarkus or Micronaut, it's in that family of technology. One of our values is high alignment with the JDK and rapid adoption. So I'll have a slide later where you see we keep quite current with the JDK. And yes, that means on some of our major releases, we're pushing forward. So we can do things like adopting virtual threads as soon as possible. Your application is just a Java SE application. So we have there's no deployment model here other than Docker and Kubernetes. Your application packaging I'll talk about later is very simple. You have a main in there. It may be ours for you or you have your own. It's just a Java SE application. We're 100% open source. We're on GitHub. Come visit us under Apache license. One thing that makes Helidon unique is we have two API flavors. So Helidon SE and Helidon MP. SE is our lower level foundational set of APIs. It's a functional, fluent type of style with builders, right? That kind of style. In 4.0, where we moved to virtual threads, it is a blocking style API, a nice, simple blocking style API. We like to say with Helidon SE, it's transparent, no magic. It's all there for you to see. You do things very explicitly. With Helidon MP, on top of SE, we built our micro profile support. So this means that you'll be programming in a declarative style. It'll be very familiar to Jakarta EE developers. So it actually includes support for some EE specifications like CDI and JAX-RS, as well as microprofile specifications. So microprofile, this was an effort from a number of years ago when Jakarta EE was stalled a bit and slow to address the microservices space. So it's a collection of specifications for things like security, config, metrics, health, tracing. And it's a specification. It says you need to implement the Jakarta EE core profile which has things like JAX-RS and CDI. It's implemented by multiple vendors, and it kind of provides a source level compatibility. So there are a number of frameworks that support microprofile. If you write an application for one of those frameworks, it ports relatively easy to another one because the collection of APIs is standardized. Helidon has a lot of features. You don't have to read this, right? It's an eye chart on purpose. So we got all the stuff. Helidon is highly modular, so we went all in on the Java module system, and we're fairly fine-grained with respect to our modules. So when you build your Helidon application, you only get the parts of Helidon you need, right? So kind of the point of this is we got lots of stuff, and it's finely grained, and it gets pulled together just what you need. In packaging, I mentioned your application is just a Java SE application. We support 3 packaging formats. Daniel, I like your slide better. I'm gonna have to get that one. But on the left, we have a simple executable jar file. This is very vanilla Java. There is a thin jar file with just your application code in it. We then have a libs directory with your runtime dependencies. The application jar has a manifest that states the main class and the class path, just vanilla Java. And you run it with java-jar. It's very container image friendly because your business logic is separate from all your runtime dependencies. With this, there are no special class loaders. There is no jar shading. It's all straightforward Java. No magic. We also support JLink runtime images. So this is similar to the first, except that our tooling supports generating a custom Java runtime. So with JLink and our support for the module system, that means when you build your application, JLink can determine what Java modules you use and produce a Java runtime with only those modules in it. And you can get up to 70% reduction, was it something like that, in terms of image size by using a custom Java runtime versus the full JDK. Our JLink support also supports CDS archives. So if you've heard anything about Project Helidon, you heard mention of CDS, which is a very early kind of generation of what they're doing in Helidon. We have support for generating CDS archives with our JLink support. That produces an on-disk cache image of class files, think of it as that, to speed up startup time. So you can get that by using the JLink image. And then we have also done some other experiments with Helidon that afterwards, if you want to hear more about that, Daniel can talk to you all about that. And we provide a shell script to help you start that application that provides some command line options to pick up the CDS archive. And then finally, we support GraalVM native image. So if you want to compile your application to a native binary, we support that as well. And then that binary obviously does not require Java runtime at all. So you can run that in a Docker container that does not contain a Java runtime at all. So there's trade-offs with each of these. Later, if you want to talk to us about those trade-offs, I am happy to do that. But we provide choice. And Helidon status, we currently have 3 lines running. If you want to look at this as tip and tail, Helidon 4 is our tip. Helidon 2 and 3 are our tail. We also have a very old tail called Helidon 1. In Helidon 2, our baseline Java version was Java 11. Our web server was based on Netty. And we supported Jakarta EE8 APIs, right? JAX-RS, that was Jakarta EE8. Helidon 3, we raised the baseline Java version to Java 17. Web server still based on Netty. The SE APIs were still reactive, asynchronous APIs. And we bumped up to Jakarta EE9. In Helidon 4, that was our big rewrite. Once again, we moved the baseline Java version to Java 21 so we could depend on virtual threads and adopt virtual threads. We replaced our Netty-based web server with a complete rewrite that was codenamed NEMA. And that's written from the socket up to be based on virtual threads. The design center for that server is virtual threads. The SE API switched from asynchronous reacting to blocking, much friendlier. And we, again, bumped our Jakarta EE support. So those are kind of the three branches we have under development and support right now. All right, now we're going to switch to virtual threads in Helidon 4. All right, so when we were planning Helidon 4, was that in 2022? We made two big decisions. One was we knew we wanted to embrace virtual threads. The second big decision related to that, but more importantly, we decided to rewrite our web server so that the design center was virtual threads. So many frameworks out there support virtual threads. Supporting virtual threads is actually pretty easy. You can kind of retrofit it on the side. It's just another thread pool you can farm off requests to. But we did not take that approach. We chose to rewrite our web server. It was a big decision. So in Helidon 4 now, the web server, like I said, is socket up virtual threads. And that means the socket that is reading a request off the network is the thread that is now dedicated to that request. And that is the thread that runs your business logic. That business logic can block that thread. That thread is dedicated to that business logic. So it's a very clean, very powerful design for a highly concurrent servers. Plus it performs great, like I said. So that's what happened when we went from Helidon 3 to Helidon 4. All right, so I'm not sure how much I like this picture, but so in Helidon 3, we were based on Netty. We had a relatively few number of Netty worker threads. Those worker threads executed your handlers where your business logic was. And we told our customers, whatever you do, do not block that thread. You need to, this is asynchronous programming. You need to make sure not to block that thread. So either do fast operations, or if you need to block, program it asynchronously, using asynchronous or reactive operators to do that. Or in some cases, maybe you need to farm it off to a supplemental thread pool. And in Helidon 3, that's actually what we did for our microprofile support. So that when the request went to Jersey, our JAX-RS implementation, there's a dedicated thread pool to handle that. So we did not block worker threads, the Netty worker threads. In Helidon 4, that all changed, right? Again, our design center was virtual threads. We now allocate virtual threads for each request that come in. So we have many, many, many virtual threads running concurrently. And as I said, your business code, your business logic can block those threads, do whatever it wants. And that has worked out great. So a very key shift. A lot of, like I said, other frameworks are kind of staying with the Netty core and adding on their virtual thread support as a supplemental thread pool. So that's what a lot of other platforms are doing. And there is a performance cost to doing that, right? To going from that asynchronous world, that platform thread, then passing that on to a virtual thread. There's a cost to doing that. We don't have that cost. So performance is one aspect of this, but the main benefit here is programming style. So these two request handlers do the same thing. They take in a server request, and then they fan that out. And there's a parameter on the request here called count that in this artificial example determines how many to fan out to, but say it's 5. So a request comes in, we want to make a connection to 5 remote services. When we get the results back, we want to take that information and aggregate it and return it as a response. So to do this in an asynchronous reactive way, there are many ways you could program this. We're showing one using reactive operators. And the code on the left is a little challenging, right? A common developer off the street might not be able to write that code. Our experience is people are not so good at writing that code and getting it correct. But it uses reactive operators. It creates a multi to get that concurrency. They're buried in there somewhere. There's a get, the client.get, which is happening asynchronously, and then we're mapping back and collecting into a list. And this code it's hard to write. It's hard to understand. If you try to step through this with a debugger, it's hard. If you get a stack trace from this code, it might not be helpful. So it's very challenging. On the right-hand side is an example of doing this in a simple blocking way. And so in this case, we come in, we use the new virtual thread per request executor service to allocate virtual threads for us. As we fan out those requests, we want those to happen in parallel concurrently. So we do that, we save the futures in a list, and then once we fan all that out and we fire off all those requests, then we loop through the futures and we do get, which is a blocking operation. And that's fine, again, because we're doing this in a virtual thread, and we just do the get, gather the responses from those remote calls, and aggregate them. So the code on the right is easy to step through with a debugger. A stack trace will make sense. If I need to modify the code on the right, it's much easier than modifying the code on the left. And the performance you get, like I said, we get tremendous performance with this as well. So you really don't lose much in the way of performance. Now, I will say a correctly coded, optimized asynchronous code very often will be faster than blocking code on a virtual thread, but almost no one writes correct asynchronous code. At least that's been our experience. I'm sure all of you could, right? I have no doubt about that, but it is challenging. So this is really the big message, that this enables the code on the right. All right, I want to quickly shift to lessons learned. So with virtual threads, one of the top topics that come up is pinning. There was a lot of hand-wringing over pinning early on with virtual threads. This happens, as I said, a virtual thread is mounted to a carrier thread to run. If it does not perform blocking operations, or maybe in some other conditions, it is unable to unmount from that that platform thread, then that platform thread is not available to other virtual threads to run. This is called pinning, when the virtual thread is stuck. The number one cause of pinning in Java 21 was use of synchronized. So there was a known limitation in Java 21 that when you were in a synchronized block, that your virtual thread could not be unpinned, could not be unmounted from the carrier thread. And therefore, if you were doing a long-running operation or a long blocking operation, you ended up blocking the platform thread. So that was not good. They have fixed that in Java 24. So that's the big message there. That is fixed in Java 24. Now, pinning is not always bad. If you're running a synchronized block, not always bad, even if you can't use Java 24. If it's just short, quick, in-memory operation, no problem. If it's during a part of your application that isn't highly concurrent, no problem. There's just a little performance penalty, right? But this is fixed in Java 24. Long-running compute-intensive operations, right? Because those aren't giving an opportunity for the thread to be unmounted, the virtual thread to be unmounted. And we'll talk about some ways to mitigate that. Those are relatively uncommon. A blocking operation in class initializers is an edge case that currently is still an issue that can cause pinning. And then I think some file operations can still cause some pinning, in which case the JVM will allocate a new platform thread for you. So those are kind of the cases that, where pinning can occur. To detect pinning in your application, you have some tools. So one is there's these kind of the original system properties for detecting pinning, which is shown at the top here. Those are not recommended for use in production, so you would want to use those while testing or maybe doing some load testing. More preferable is to use Java Flight Recorder, which now can produce events for pin threads. And there's thresholds and conditions that will trigger the event that you have some control over, but you can use Java Flight Recorder for detecting those. We also have pinning detection built into Helidon 4.2. So we have a feature Helidon Test. And when you write tests with Helidon Test, you can request that we detect pinning for you while the test is run. Daniel wrote this, by the way, up front. So you can enable this for your tests and then have pinning detected that way. We actually found a couple cases where we were pinning in Helidon with this. So it is valuable. Of course, not with Java 24, we wouldn't. And then Helidon metrics, using JFR events, you can enable this and we will report some virtual thread metrics, including number of pin threads if detected. So those are a couple of Helidon ways for pinning detection. For tips, the number one tip to avoid pinning is to use Java 24. You can replace synchronized blocks with reentrant locks if you can't use Java 24. Be careful with concurrent hash map. This is one thing early on where we detected some pinning that we were doing before Java 24 was in concurrent hash map. So most operations in concurrent hash map is fine, but it does use synchronized. So there are some methods that you can provide a lambda to, the methods that start with compute. And if your lambda does a blocking operation or something slow, that can cause pinning if you're not using Java 24, because it will be executed in a synchronized block. Yes, the big hammer, offload work to a platform thread pool. So if you know your workload would best benefit from a platform thread, like maybe you are doing a set of highly intensive compute operations that you want to isolate from the rest of your server, and you want to do those in a platform thread pool, then by all means, right, do those in a platform thread pool. And then tuning parallelism. I mentioned there's a thread pool where virtual threads are scheduled onto. You can have some control over the size of that thread pool. The parallelism sets, I think, the minimum thread size for that pool. What we have found is on very low core count VMs, you may want to bump that up a little bit. If this happens to be set to 1, you can kind of imagine cases where that would be trouble. So we have found on very low core count machines, maybe bumping that up. Similarly, if you have kind of a big server on a big machine, but it's under light load, you may want to bump that number down because the more platform threads there are, the more work the scheduler does to schedule. So if you know you have a light workload on a big machine, you may want to tune the parallelism down. All right, I mentioned one approach you can have for some workloads is offload them to a thread pool. So we have some mechanisms to help you do that in Helidon. With MP, declarative style, we have an execute on annotation that you can put in a bean on a method. And that says execute this method on another thread pool. And you have some control over what that thread pool is and how it's configured. Here it's just using default settings for a platform thread pool. So our pi digit calculator, that method will run on a platform thread in this case. Similarly in SE, you do it a little more fluently, explicitly by using our thread pool supplier. And you could set virtual threads to false, which means it will allocate platform threads. Thread local variables, you need to keep an eye on these and be careful with them. You can use them. Virtual thread supports thread locals, but be careful with them and think that instead of a handful of threads that are reused, I'm going to be creating thousands, hundreds of thousands, millions of threads. So there are cases where thread locals make sense. We use them in Helidon to pass request context along. So in that case, it makes sense. But to do some expensive computation and cache the result as a big blob of data on a thread doesn't work as well with virtual threads, because usually after that task is complete, the thread's thrown away. So you're just getting the expense with no reuse. So you can use thread locals, you just need to be careful how you are using them. And coming up, JEP 487 scoped values, I think they're hoping this will be final in Java 25. This will be the correct way to do thread locals. It's in preview now, scoped values. Okay, rate limiting. So if you have virtual threads and you're allocating them unboundedly, then you're drinking from a fire hose. And in the old days, your thread pool, your threads were the limiting factor. So your thread pool acted as a rate limiter often, as a throttler, as something that would throttle, right? Because you would exhaust the thread pool and requests would back up. So with virtual threads, you need to do that independently because there is no throttling based on threads because they're pretty much an unlimited resource. So I'm going to quickly go through a couple mechanisms here. One is using a Java semaphore. This is a very low-level approach to doing that. And the semaphore API is actually pretty rich. So what we're doing here is we have a semaphore, we create it, we say permits 10, which means to allow 10 concurrent requests or 10 concurrent acquires to occur. When we do sem.acquire, the thread will block until a permit is available. And that in a virtual thread is fine, right? And then once the work is done, you can release the thread. Semaphore has a number of other options. You can choose to block or no block or not block. You can get an estimate of how many other people are waiting. This allows you to implement things like backlog queues using semaphores. So it's a pretty flexible mechanism that will work anywhere. In Helidon, we have a number of features to help with this. So we have a very simple, blunt, global feature, a max concurrent requests. So if you set this in your configuration for the Helidon server, in this case it's set to 1,000, then when the server has 1,000 concurrent requests running, it will start rejecting requests with a 503. So this is a very simple mechanism to put a cap on the number of concurrent requests. We often recommend you set this above your expected burst load on your application. So it's kind of a safety net, right? A ceiling that you know your server won't go above. We have more sophisticated rate limiting features for handling concurrency. These again are global to the server, but there are two algorithms. One is kind of a fixed algorithm, which will look kind of a familiar pattern. You say how many concurrent requests you want to handle and how deep you want your backlog queue to be. And then web server will then do that rate limiting for you. We also have an adaptive algorithm, which is adaptive. So you set an initial limit for how many concurrent requests you want to occur. The server, as things are working successfully, will start to bump that up. And then once congestion is detected or requests start to time out, right, the server cannot handle the load, then you have a back off where the limit is reduced for you. So that's more adaptive. So currently we support those two algorithms in this feature. Okay, so those were kind of global. So I want to now look at a Helidon feature that's more targeted to code. And this is using a feature called bulkheads, which are often a capability in fault-tolerant frameworks. And the purpose of bulkheads is to protect code that is using a scarce resource. So if you have some handlers, some endpoints that maybe are accessing a database or doing expensive database operations, you can put a bulkhead in front of that code and then limit the amount of concurrency in just that code. So a bulkhead, again, lets you set a limit for concurrency, the number of concurrent requests, and a backlog queue size for that. And then as you go into submit a request to the bulkhead. That thread, if there's not room, it'll block. So very similar to a semaphore, just a little easier way to structure it. In MicroProfile, we support this via declarative annotations because this is a feature of the MicroProfile specification. Okay, so I kind of described a couple global mechanisms for managing rate limiting and concurrency at a global level. And then you can use semaphores or bulkheads, which are a little friendlier, to do it around specific code, right, that you want to protect. We're going to look at some things that are in the works or coming up. I mentioned the synchronized keyword issue was fixed with pinning in Java 24. You can look at JEP 491 for more details. There is also a good Inside Java newscast, number 80, if you want to watch a video concerning this. That's pretty informative. So there are still some cases where pinning can occur, but they tend to be fairly rare edge cases. And in fact, all the pinning issues that we ever saw during our development of Helidon 4 are, I think, completely addressed by JEP 491. So a couple of the JEPs to watch. I mentioned Project Helidon, which is ahead of time processing being done in the JDK group. They have now kind of a foundational approach to this, and over time they will be adding capabilities to that, basically shifting more and more processing to build time so that it doesn't have to occur at runtime. And the whole point of this is to minimize the time from startup to first response and startup to maximum performance. So that's Project Helidon. So keep an eye on that. Scoped values, this is the, as I mentioned, the alternative to thread local. I think they're hoping to get this final in Java 25. So keep an eye on that. So it's just a more formal, organized alternative to thread locals. So pretty much better in every way. Structured concurrency. So this is in 4th preview in Java 24. I don't know what the odds are of it getting final in Java 25. This is a way to let you structure tasks. So if you think about all these virtual threads you spin off, you can group them in groups and then operate on the groups. Plus, I think there's additional features. So structured concurrency is another JEP to keep an eye on. Helidon 4.2 was just released this month. So in that release, we rounded out our Java 24 support. We have improved virtual thread support. I mentioned some fixes that went in. I mentioned monitoring and testing, improved testing support. We have a few preview features. We're a preview feature for Helidon injection. So this is looking at adding injection support to our SE API. And the thing that makes Helidon injection unique is it is source code first. It is completely build time. And at build time, source code is generated, not bytecodes, and it's not bytecode manipulation, and it's not runtime discovery. So it's all ahead of time, all build time, all fully deterministic. And in fact, you can look at the source code of our injection framework, right? So that's pretty unique. LangChain for J integration. Daniel went over this in his talk earlier today. That is kind of a proof point for Helidon injection. These are previews, so we want to do a significant feature based on them. And then crack support. That's a coordinated restore at checkpoint. So this is an OpenJDK project. It's another way to improve startup speed. Crack operates on a suspend and resume model. So if you're running with Helidon's crack support, you can suspend the VM, which will quiesce it and suspend it, and then later resume it, at which point it starts almost instantly where it left off. So that's crack support. Okay, so here's a summary of sessions. The top 3 are done. We now have 2 hands-on labs. So this afternoon, if you want to play with Helidon and our AI support with Lang4j integration, that's this afternoon. And then tomorrow morning, we also have a repeat of that hands-on lab. Come visit us. If you go to helidon.io and go to the starter, you can have a Helidon app up and running in 30 seconds, as long as you have Java 21 or newer and Maven. Or come see us on GitHub. We'd love to interact with you there. So with that, I guess we have a couple minutes for questions. Yes, sir.
Joe, I don't have a question, but since there weren't a lot of hands that said they used Helidon, I thought I would do a little sales pitch.
I love it. First of all, what's your name?
My name is Richard Bear.
Okay.
I was at Oracle on the Java team for a long time, a Java client, and then I went to IoT, and on the IoT team, we built on top of Helidon, loved it. It's all Helidon 3. And my current role, I lead an engineering team with our product is one of our guys uses Netty, the other one's using Helidon, and we're going to convert the other one to using Helidon too.
Yay! Helidon.
The move to virtual threads is awesome. That was one of the primary drivers. Also, since I've used Helidon before, I knew it was great. The other one is I went and read the source code, and it is really clean. It's really good. I was able to take, we're trying to reduce the number of dependencies that we have. And so I would go look at like Netty, and there's just this massive number of dependencies. And I went to Helidon and I said, if I just take a Helidon SE and carve out the pieces that I need, I was down to a couple hundred kilobytes for a fully functional virtual thread high performance web server. I was like,
yeah.
So anyway, little sales pitch for anybody who's trying it. You should absolutely try out Helidon.
One of the benefits I didn't say is the development team loves working on Helidon 4 code base. And
it's super clean.
Every time we have to go back to Helidon 3, which is based on Netty and asynchronous, everyone gets a little stomach ache. So nothing wrong with Helidon 3, but even our developers love working with virtual threads and in a simple blocking style API. And I think our implementation has benefited from that, for sure. Nothing against the awesome reactive operators, Daniel, that you did. But that's been, okay, any questions? Yes, sir.
Okay, in my company, we are usually an OpenShift strategy using Quarkus. How is the support of Helidon if we can deploy over OpenShift? Is pretty neat using Kubernetes?
Oh, using Kubernetes on OpenShift? Mm-hmm. Oh, yeah, yes. So
how is the performance of Helidon instead using Quarkus, for example, using Kubernetes as a microprofile?
Right. Yeah, that's a loaded question. So, and it's loaded because Quarkus has some reactive optimizations with Netty where they're essentially vertex. And if you look at like the Tech and Power benchmarks for Vertex, they're spectacular because they have a highly optimized, correct asynchronous application. So there are scenarios of Quarkus that, if you look at Tech and Power, look blindingly fast, very fast. But in the real world, what we have seen, and I'm not prepared to show numbers, is under highly concurrent loads, we provide tremendous performance and, more importantly, very stable latency. So when you start to get loaded, you don't get these spikes that we see in asynchronous frameworks, where some requests are handled almost instantaneously and other requests have a lot of latency because they're backed up on waiting for the threads. And when the machine gets saturated. Where we see the latency with virtual threads is just very stable and consistent, and excellent too. So it's kind of hard to say, right? Raw throughput with like a vertex-based application, which you can kind of shape Quarkus into, it's hard to beat on optimized benchmark stuff. But But yeah, in general use, we've been very, very happy with our performance.
Okay.
Yes.
Another option.
Yeah, it's an option.
It's an option.
We're all about choice. Anything else? Okay, I know we're headed into lunch. My colleagues and I will be around. So thank you.